we've covered some limits of infinity at infinity in general. We've talked about them for rational polynomials, but there are significantly more functions in the world than rational polynomials. So we're going to take a look at some different functions involving some trig, some square roots, and try to see if we can't develop some additional techniques on analyzing these functions at infinity. And what you'll find is it's really a variation on a theme. So the first one is this square root function. So I've got an x to the 10th on the top and an x to the 8th on the bottom. So the way that I like to think about these problems is I like to think about them in terms of their effective degree. Okay, so what does that mean? Well, the largest degree, what's going to happen here, okay, let me take a step back. What happens here is that these polynomials, the largest degree term dominates, because as you get really large, the cubed function, for instance, is going to dwarf the squared function. It's just going to run away so much faster, right? At x equals 100, x cubed is 100 times larger than x squared. At 1,000,000, it's 1,000,000 times larger. So that largest degree is going to dominate, just dominate that term. So what that means is that when you're looking at going towards infinity, you don't have to worry about that -1. You really only have to worry about that x to the 10th. But the big thing is that we have this square root. So what the square root is it's a 1/2 power, right? You can write that as a 1/2 power. And so if you have something to the 10th to the 1/2, its effective power is x to the 5th. So it's, from long-term behavior, it's going to behave very similarly to x to the 5th. So as a result, you can kind of keep that in the back of your head as you look at this. You say, okay, well, this is roughly x to the 5th on top. This is roughly x to the 8th on bottom. So I know that the bottom term dominates. So how do I prove that this thing's going to go to 0? Well, what I can do is I can say, well, what I'm going to do is I'm going to factor out and let's just say an x to the 6th, right? Let's pull out an x to the 6th. We're going to say I'm going to multiply top and bottom by x to the 6th. Or 1 over x to the 6th. Now, when x to the 6th goes inside the square root, it becomes x to the 12th. Oh, again, we're going to negative infinity here. Well, whatever. So that becomes 1 over x squared minus 1 over x to the 12th, all over x squared minus 1 over x to the 6th, right? And anywhere you find a 1 over, the 1 over something will go to 0 as x goes to infinity. So that's like 0 minus 0 over infinity minus 0. Well, if you have an infinity, if you have an extremely large number on bottom, then the whole thing is just 0. And that's kind of the rough idea. So again, because it has that effective degree, you could kind of say, okay, well, this is x to the 5 on top, this is x to the 8 on bottom. I know the bottom degree is larger, so I know it's going to drive to 0. That would also be perfectly acceptable. All right, let's move on. Our second one is this, 7 over 4x plus sine of x. This has a problem because sine of x has a wave. It doesn't actually converge to a number. It goes up to 1, down to -1. That's all you've got. But I do know this about sine of x. It never goes below -1, and it never goes above +1. So it's always bounded. It's always bounded. But this isn't bounded. This thing gets massively large. So this doesn't change. This is bounded, and this is unbounded. So as a result, it just goes to 0. The reason it goes to 0 is because this thing's going to get infinitely large, and this can't do anything to stop it. It's going to get so big, this thing's just going to dink it, and it's just going to eventually drive way, way, way past any value that we could, or drive below. This value is going to get large, so the one over the value is going to drive straight to 0. So next one we have sine of 6x over x. And if we were going to 0, if x was going to 0, we could use the squeeze theorem and we could analyze that. But we're not going to 0, we're going to infinity. But this is the similar case to this. What I know is that my top value never goes above 1 or negative 1. Now it does change from negative to positive, so we have to be careful. But what I see here is that this thing is bounded and this is unbounded. So x just gets massive, which just drives it down. The whole idea is you got to think about if these two things are in a race, and this thing is racing way off to infinity, and this thing is basically driving in a circle, then this thing is going to way outpace it. So the ratio of the value that this can have to the value that this can have, this thing just completely overpowers it, drives it to 0. Over here we have something that looks similar to this but actually behaves completely differently. And that's because it's the cosine, the x is inside the cosine. Now if you remember about continuous functions, that if you're taking a limit of a continuous function, you can pass the limit inside. Remember, this is equivalent to saying 3 cosine the limit as x approaches infinity of 5 over 6x. I don't know if you remember that, but it's a continuous function, so we can pass the limit inside. Since we can pass the limit inside, this is just a standard rational polynomial, and we know that something over x just drives down to 0. So this becomes 3 times the cosine of 0, which is 1, giving us a final answer of 3. And this one's a little more complicated. If I were to look at x going to negative infinity here, what I would see is that this goes to negative infinity and this goes to positive infinity. So what I have is like negative infinity plus positive infinity, which is what we call an indeterminate form. It's not really well defined. So we have to use some algebraic tricks to see if we can't re-describe this in a way that is a lot more meaningful. And so we're going to do that by using that conjugate method. So if I'm going to rewrite this as the limit as x approaches negative infinity of 5x plus 25x squared minus x over 1. And so since we have that, we have some sort of a plus the square root of b. And if you remember from our previous discussions on limits, we have a plus the square root of b. We can multiply by a minus the square root of b. So we can say 5x minus 25x squared minus x. 5x minus 25x squared minus x. And so what we're going to do is we're going to leave the bottom alone, and we're going to say, all right, the limit as x approaches negative infinity of 25x squared minus 25x squared minus x all over, right, because that's going to be a squared minus b squared, and that's going to be 5x minus the square root 25x squared minus x. So what you're going to find is these 25x squareds are going to cancel. You're going to end up with the limit as x approaches negative infinity of x over 5x minus the square root of 25x squared minus x. So you're going to have that. Now this is where things get a little bit interesting. If you look at this, it's like an effective degree of x squared, but then you have that to the 1/2. So this is like an effective degree of x, an effective degree of x, an effective degree of x. So let's just divide everything by x here. Let's multiply top and bottom by 1 over x. So that gets us 1 over 5 minus, now if we multiply 1 over x in here, again it translates through as x squared, or 1 over x squared, because of the way the square root works. So then we have 25 minus 1 over x. So as x goes to positive infinity, or negative infinity here, let me check my notes. I've got something different written down in my notes. So if I multiply by 5x and 5x and negative here, I should get 25x squared minus, technically that becomes an absolute value. As that goes to negative infinity, though, that's basically the same thing. Those cancel, I get a positive x. Multiplying by 1 over x, I get this. So this goes to 0. This becomes 5 minus the square root of 25, though, right? So that should be 1 over 0. But this is technically going, what you're going to find is this is going 25 minus 1 over x. So this is where things get a little bit fishy. You have to be a little, like, real careful. So x is going to negative infinity, right? X is going to negative infinity, which means that negative 1 over x is just a little bit larger. This is going to be equivalent to, maybe this is better to say, this is going to be equivalent to x going to positive infinity of 1 over 5 minus 25 plus 1 over x. And what you're going to find is this is a little bit larger than 25. So the square root's a little bit larger than 5, but not by much. And it's 5 minus something a little bit larger than 5. So it's 1 over like a negative, like a really small but negative number. So you're going to get negative infinity. Now, I want to be careful here because in my notes, the answer to this is listed as 1/10. And I'm going to be honest with you, I do not understand how that could be true. It's possible, clearly it's possible, I've made a mistake here. So be careful, this may end up being 1/10, but from the way I've worked this, I arrive at negative infinity. So when you're working these types of problems and looking, be careful. It's possible I missed something, but this is still the basic process. This is the idea of how you would do this, but there may be some small detail that is missing from what I've done that makes it incorrect.